Hello, constant biochemist. Today I want to talk to you about maybe one of my favorite topics in all of biochemistry, and that is inhibition. Now, what I'm going to focus on today is I'm going to be focusing on one specific type of inhibition, and that is known as competitive inhibition. So imagine that we have an enzyme, and that enzyme has a substrate. And that enzyme, whenever it sees the substrate, goes on to form an ES complex. So it binds to that substrate. And, well, whenever that ES complex is formed, it's pretty much a foregone conclusion that we're going to get our enzyme back and we're going to get the product. Okay, now you could kind of look at this as, I don't know, two steps and then conclusion. The first step is the enzyme and the substrate both have to be present. The second step is the enzyme and the substrate have to form that complex. And then the conclusion is the release of that product. Well, a competitive inhibitor, I like that word competitive. What it's going to do is it's going to see the opportunity to disrupt this whole system. And the way that it's going to do it is by competing against the natural substrate. So whenever we talk about a competitive inhibitor, we're going to label it, or any type of inhibitor, we're going to represent it with the letter I. Well, what a competitive inhibitor is going to do is it's going to insert itself whenever the free enzyme is available. And it's going to try to bind to the active site because, heck, the structure of I and S are very similar. They're very similar in shape. They both have the ability to bind to the enzyme's active site. Now, in the event that you form this enzyme plus inhibitor complex, represented as EI, well then, you're not going to form a reaction. Basically, no reaction is going to take place. It's just going to kind of reach a dead end there. As opposed to if the enzyme binds to the substrate. If the enzyme binds to the substrate, well, then it can proceed along and generate the product. Now, whenever we're talking about our enzymes and we're talking about different types of inhibition, we will always want to kind of look at are the kinetic parameters of Km and Vmax. Now, if you need a little bit of a refresher on those, I've got a video covering those two kinetic parameters. But your Km, that is a measure of your affinity, the affinity that your enzyme has for your substrate. Vmax is the maximum velocity that your enzyme can catalyze a reaction at. Okay, so when we talk about inhibitors, what we're always curious about is what happens to the Km and the Vmax. Well, one thing that I mentioned just a second ago is that as soon as this forms, as soon as the enzyme comes in contact with and forms a complex with the substrate, the product's going to be generated without an issue. So your Vmax is unchanged. Now, when it comes to affinity that your enzyme has for your substrate, well, that's actually going to be changed in the case of a competitive inhibitor. Because let's say that we have an equal shot at binding the inhibitor or the substrate. Let's say that you have, 3 copies of the inhibitor. Well, if your enzyme is equally apt to bind substrate or the inhibitor, and there's more inhibitor present, well, it's going to go ahead and bind the inhibitor. On the contrary, if you add tons and tons and tons of substrate, what's going to happen? What's the likelihood that you're going to form that ES complex? Well, it's going to go up. So if you increase the substrate concentration, you can increase the likelihood of that ES complex forming. So what that means is that your Km is going to increase. It's going to increase Because what you're saying effectively is if I have more and more supply of my substrate, I can reach my Vmax. I can reach half my Vmax, but it takes more of that substrate. Okay, so Km is going to increase, the Vmax is going to be unchanged. Now, whenever you look at a competitive inhibitor and it's plotted, I'm going to plot a competitive inhibitor on a Lineweaver-Burke plot, LB, and a Michaelis-Menten plot. Okay, the labels for my Michaelis-Menten plot are V sub 0, substrate concentration. For my Lineweaver-Burke, it's 1 over V sub 0 and 1 over substrate concentration. Now, what I'm going to do is I'm going to use the blue line to depict my no inhibitor present situation. So there's a line that shows no inhibitor. Okay. Then on my Michaelis-Menten curve, got that same sort of plateau type of effect. I reach my Vmax. Okay, there's no inhibitor. Okay, now I'm going to switch over to use, let's go with a orange line. Orange line to depict with the inhibitor present. Well, let's think about our parameters. When we talk about a Lineweaver-Burke plot, the y-intercept is 1 over Vmax. My Vmax is unchanged, so my y-intercept is going to remain the same. What is going to change and what is going to increase is my Km. But remember, looking at our x-axis shows that's where we're going to find our Km, but our x-axis is the inverse. So what that means is that my number, or my Km, my plus inhibitor line, is going to look like that. My slope is going to increase in a Lineweaver-Burke plot. Okay, so I'm going to have an intersection of my two lines, my no inhibitor and my plus inhibitor along my y-axis. Now, what is this situation with an inhibitor present, a competitive inhibitor, look like on a Michaelis-Menten plot? Well, the only thing that's going to change is my Km. My Vmax is not going to change. So that means I'm ultimately going to reach that same plateau region, but I'm going to have a curve that looks a little bit like this. Okay, so I'll say plus I right here. And in the event that you're looking at that and thinking, well, that's a little bit confusing, keep in mind, half of Vmax. Well, here's my Vmax. Here's half of that. Extrapolate out to line up with my blue line. Here's my Km. Then to this line, here's my Km. I'm going to label it prime because I have an inhibitor present. So my Km has increased because I've moved to the right along my x-axis. So there's our two different graphs. A competitive inhibitor structurally looks very similar to the natural substrate, or at least a portion of it does, so that it can line up and interact with the active site of our enzyme. Well, I hope this was helpful. I hope this filled in some gaps, and I hope that it helped you visualize on a Lineweaver-Burke and a Michaelis-Menten plot what a competitive inhibitor looks like. Well, have a good one.